So hello, today we're going to look at vectors as velocity or velocities as vectors. So let's see what questions were given. So an airplane is heading north at an airspeed of 600 kilometers per hour. In part A, if the airplane encounters a wind from the north at 100 kilometers per hour, what is the resultant ground velocity of the plane? All right, so let's draw in some of these vectors. So first we have a plane heading north at 600 kilometers per hour, and this is north. This is our plane, so we'll call this VP. And we have a wind that is coming from the north, wind from the north at 100 kilometers per hour. Let's use a different color for that. So there's the wind. So if it's coming from the north at 100 kilometers per hour, it's actually going down south. So it's heading in the opposite direction of our plane. So what is the resultant ground velocity of the plane? So now we need to add our vectors together. So let's use a different color. So we have our plane is going north. Our wind is actually going south. So our resultant vector is this green one. And the magnitude of the green is actually 600 minus the 100. And it's minus, so we can write that as VP minus VW, because VW or the velocity of the wind is actually in the opposite direction of the velocity of the plane. So we actually have a resultant vector of 500 kilometers per hour north. Okay, so that's part A. But part B, if there's a wind from the south at 100 kilometers per hour, what is the resultant ground velocity? All right, so now in this case, let's scroll over. Oh, let's correct that, resultant ground velocity. All right, so now in this case, let's part B, our wind is now coming from the south at 100 kilometers per hour. So let's call this V W prime. So VW prime is actually heading in the same direction as the plane. So now when we add the velocities together, we have our plane, so it's 600 kilometers per hour north. Our wind is also going in that same direction, but at 100 kilometers per hour north. So our resultant vector, which is VW prime plus velocity of the plane, is actually 600 plus 100, or 700 kilometers per hour north. Okay. Good. So the wind in this case is actually helping the plane. Just labeling everything. There you go. And that's part B. All right, so let's have a look at the second question. So we have a motorboat traveling 4 meters east, and it encounters a current traveling 7 meters north. What is the resultant velocity of the motorboat? In part B, if the width of the river is 80 meters wide, then how much time does it take the motorboat to travel? Oops, where is it? Shore to shore, so from one side to the other. And part C, what distance downstream does the boat reach the opposite shore? All right. Okay, so I've actually put together a little diagram for this already. So we have our motorboat. This is our boat. There's our boat. It's not exactly a motorboat, but that's our boat, and it's going east 4 meters per second. Our stream is flowing north 7 meters per second. we want to find our resultant vector. So in part A, what is the resultant velocity of the motorboat? The motorboat's going to be pushed by the current, so we need to find R. So we do know we have right angle triangle there, so how do we find the magnitude of R? Let's start with that. We use the theorem of Pythagoras. So let's start with that one. So let's scroll over, make it a little smaller, and let's label some of these things. We'll call this velocity of, let's call it velocity of boat and velocity of stream. All right. Okay, so R, magnitude of R squared is let's do this. Magnitude of R squared is a square root of magnitude of boat squared plus magnitude of the stream squared. Let's plug everything in. That's part A. And we have 4 squared plus 7 squared. So we have square root of 16 plus 49. And let's punch that into our calculator. Square root of 65, it's just approximately 8.06 meters per second. So that's the magnitude of our resultant vector. Now we need to find the direction. So why don't we do the direction in relation to how about we do that? We'll look for this angle here. So it'll be either northeast or southeast. So let's have a look at our angle. So tangent of theta is opposite of our hypotenuse, or 7/4. So that means theta is tan inverse of 7/4. Again, we'll just punch this into our calculator and see what we get. All right, so then theta is 60.26 degrees approximately. So our resultant vector is, let's write this down, therefore R equal approximately 8.06 meters per second squared. And let's see, how do we actually, how should we write this? It's usually conventional to write it as northeast. So let's figure out this angle here. So that angle is actually 90 minus 60.26. This angle right here is 29.74. So north and 29.74 degrees east. Yeah. So we're going northeast. Good. So this is our resultant vector, 8.06 meters per second, north 29.74 degrees east. Okay, so we have that. Excellent. So now let's look at part B. If the width of the river is 80 meters wide, then how much time does it take the boat to travel shore to shore? All right, so let's go back to our diagram. Okay, so from shore to shore, if our boat is going straight across, and that's 80 meters, we need to consider the velocity in that direction, which is 4 meters per second. So B, and how do we find time? So velocity or speed is distance over time. We're looking for time, so we're going to solve for time. So it's distance over our speed or velocity. Our distance is 80 meters. Our speed is 4 meters per second. So I'm just going to do that division and see what we get. And we get 20 seconds. So it takes 20 seconds to go from one side to the other. Okay. However, in part C, what distance downstream does a boat reach the opposite shore? So if we look back at our diagram, if our boat is traveling across, yes, it'll take 20 seconds, but the current of the river is going to push it. So it's going to be pushed in this direction. North, it's going to be pushed, I think, north 29.74 degrees east. So we need to figure out how far downstream we've traveled. So in this case, we use the velocity of the stream with that period of time, so 20 seconds. So let's find a little bit of space. All right, so part C, we know our velocity of the stream is 7 meters per second north. We know our time is 20 seconds. So to find our distance downstream, we're going to use our formula and do our speed times our time. Let's do that. 7 meters per second times our 20 seconds. And that gives us 140 meters. So we've now traveled 140 meters downstream. If we go back to our diagram, this distance traveled is 140 meters. Good. All right. So that looks like we've come to the end of our session today. So if you have any questions, feel free to give us a shout at info@raisemymarks.com or give us a call day or evening, and we'll be happy to help you. Thank you for watching.